Hey everyone, Professor Dustin here, and this is going to be a solution to a whiteboard problem called atomic potential. So here's the situation. We have a potential energy graph right here, which is a plot of the energy in units of 10 to the minus 21 joules. So we can kind of ignore that, right? These are just the numbers, and this is the scientific notation to tell us that they're actually very, very small, but this tells us the units, and really don't have to worry too much about that. So that's the energy as a plot of the distance. So these are like two molecules separated by some distance x. Let me try to get a nice little picture of that. So that's kind of what we're talking about. Two molecules separated by a distance x, which is given in nanometers. And you can see the tick marks are 0.1 nanometers each. So the energy goes from like 30 down to minus 20, back to 20, and then down out here. And you can see it says V effective. That's really because like the potential energy interaction between two molecules is actually quite complicated. So this is sort of like an approximation, but for the purposes of this problem, we can just say this is the exact potential energy. Okay, so the first part says, draw a quantitatively accurate graph of the force acting between these two atoms as a function of x. So for this, we have to remember that we have this basic definition, which is that the force is the negative derivative of the potential. So that's sort of a thing we have to memorize. We can think carefully about it by thinking about what happens when potential energy changes, but we can also just think of this as a formula which is given to us. So graph, we basically want to reproduce the exact graph we've got there over the same range. So this goes out to 0.6 nanometers. And if we want to make a plot of the force, we want to find the derivative of u at every point in this graph. But of course, the derivative is just the slope. So finding the derivative of the potential of this graph is just a matter of finding the slope at each of those places. Now the slope everywhere between like 0.1 and 0.2 is going to be exactly the same because it's just a straight line. So we really just have to find the slope at 1, 2, 3, 4 different places. So I guess what I'll do is I'll just label those regions 1, 2, 3, 4, and then we're just going to find the rise over the run of each of those specific places. So for 1, it's going from 30 to minus 20, so that means it drops by minus 50 over a distance of 0.1 nanometers. So divided by 0.1 means multiplying times 10, so we get minus 500 as the answer there. For 2, the region 2 right there, it's got a slope of 0, right? It doesn't go up or down, so that's a slope of 0. For 3, it goes up from minus 20 to positive 20, so it goes up 40. And the x distance is 0.1 again, so that's 400. And for the 4th region, it goes down from 20 to 10, so it goes minus 10 over a distance of 0.4, 0.5, 0.6, 0.7, so 0.3. So 10 divided by 3 is, 0.3 repeating, times 10, so that becomes 33 minus 33.3. So I want to plot that. We can see the total range, the maximum range is 500. So I'm going to put that on my plot as, 500 there, minus 500 there, and try to put 5 tick marks. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Doesn't have to be too good, just sort of want to get that approximate. That's minus 500. And now I'm just going to plot over the first region, which goes from 0.1 to 0.2. So from here to there, we have a constant value of minus 500. Now, of course, we have to be careful. There's a minus sign in the actual formula here. So while we've calculated the slope, this is du dx in that region, we have to throw in another minus sign to deal with the force. That's because if the potential is increasing, that's a positive gradient. The force has to oppose that because as the potential increases, the object wants to go in the opposite direction of that. That's where that negative sign comes from. So anyway, minus 500 becomes positive 500, constant over the entire region. And I'm going to write it like this to make it clear that, we can't take derivatives at points that look like that, right? That are kinks like that. We can't actually take derivatives. So I don't actually know what the derivative is at 0.2, but I know that the derivative just before 0.2 is a constant 500. In region 2, it is 0, so it goes something like that with 2 circles on either side. Region 3 goes to 400, that's minus 400, so it goes down to here. like that, and then it goes to minus 33. That's positive 33, so just a little bit above the axis until the end of the diagram. So it actually goes out to 0.7 like that. Okay, so that's the answer for part A, showing the gradient of that potential with a minus sign, and that tells you the force that these objects feel as they move closer and further apart from each other. Okay, so that was part A. Part B says, if this system had a total energy of minus 10 to the minus 21st, where would the turning points, allowed regions, and forbidden regions be? So I want to sort of focus on the graph for this. So what's really important is that it's telling me what the energy is. I need the energy in order to answer this question at all. The easiest way to do this is to just notice the energy and then label the energy on the diagram. So this is a plot of energy. It's showing us the potential, but if the total energy is minus 10 times 10 to the minus 21st, that means that we can draw a constant line of total energy right there, E, to indicate what the energy is right now. So this is the potential energy of the system, but the system can have any given energy that it wants to at any given time. Basically, just pump energy into it until it gets to that level. Okay, there's a minus total energy in here, but that's not a big problem because, of course, potentials can be negative. So the total energy could be negative if the potential is indeed negative. Of course, that's not true for the kinetic energy. The kinetic energy is 1/2 mv squared, must be positive. So anyway, we're going to indicate the turning points. So the turning points are the intersection points between the energy and the potential. So in this case, we have only 2 intersection points. And we always need the energy to be larger than the potential. That means that the kinetic is positive. So actually, basically in this region, since the potential is minus 20 and the energy is minus 10 in most of the region, we can actually say that the kinetic energy is basically 10 times 10 to the minus 21st. Yeah, on the edges, as the potential rises, the kinetic energy is going to go down. But essentially, the energy is minus 10 in almost the entire region. The potential is minus 20 in almost the entire region, and so the kinetic is essentially 10 in the entire region. Okay, anyway, so we can now indicate allowed regions, which are between the points. This is allowed. And then forbidden is outside. So the entire region less than 0.2 and greater. Of course, it's not exactly 0.2. You know, it's like a little under 0.2. It's a little over 0.3, whatever. Those outside regions are forbidden. So that's the answer to part B. Okay, so now part C is very similar to part B in that we now have a different energy level, and we want to also indicate where the turning points, allowed regions and forbidden regions are. So again, I want to try to focus on the figure, and we have a new energy which is plus 15. So I'm going to indicate that in the picture by just a constant line going straight across the diagram. That's the energy level is at plus 15. And so now the turning points are the intersection points between the energy and the potential. They are right there, there, and there. Those are the turning points. And now the allowed regions are wherever E is greater than U. And so that is going to be inside here, allowed. Because you can see the potential is going down over in this entire region. The energy is above the potential. And also outside here is also allowed, because also out here, the total energy is above the potentials, meaning that in these regions, the kinetic energy can be positive. Indeed, it has to be positive. In between, meaning closer than whatever that intersection point is, those regions are forbidden. Because potential energy is above the kinetic, and that implies that the potential energy is above the total energy, and that implies the kinetic energy is negative, and that cannot happen. So those guys are forbidden. So the last part of this question says, assume the system has a kinetic energy. So now instead of telling us the total energy, is telling us the kinetic energy of 5 times 10 to the minus 21st. The atoms are separated by that distance, and they are moving towards each other. So there's a fair amount of information packaged into that one sentence. Describe what happens to the 2 atoms. So we always have to go back to finding the total energy in order to answer this question. We can't just use the potential or the kinetic by themselves. But of course, I think we have enough information here to actually answer what the total energy is. We know what the kinetic energy is, which which is right here, and we're being told what the position of the objects are. They are separated by 0.7 nanometers. 0.7 nanometers is on the plot. It's right here. So that means this is the location of the molecules right now. That means that they have a potential energy of U, which I can just read off this as being about 10 times minus 21st joules. Okay, so now since energy is K plus U, this tells me what the total energy is, which is 5 plus 10 times 10 to the minus 21st joules. And so the total energy right now is 15 times 10 to the minus 21 joules. So now we just repeat the same logic we used before. 15 is right here. That actually is the situation we were in part C, so we could actually go back and look at that. But we want to describe what is happening to the two atoms if they are moving towards each other. So let's put the turning points on here. That's the intersection points between potential and energy and total energy. So they are here. They are at this location. They are moving towards each other. So that means they're going towards less and less separation. Remember, these two atoms are separated by a distance x. That's what's being indicated in the x-axis of that diagram. So they're going towards each other like this, right? X is getting smaller. So they're going to keep doing that until they hit the turning point, right? Once they hit the turning point, their kinetic energy cannot be negative. So their kinetic energy is getting less and less as they go towards each other. But at some point, their kinetic energy reaches zero, and their kinetic energy cannot get any less than zero because kinetic energy cannot be negative. So once they hit that point, they get there, they can't go any further, so they have nothing to do but turn around. And so they turn around and go back the other way. So that's the answer to this question, which is that they turn around and go back. Now, we would have to think about what happens after they turn around. We don't know what the potential energy curve looks like outside of that region. So all we can really say is they go back and they go outside of 0.7, right? Because we don't know anything beyond that side of 0.7. Usually what happens to molecules is once they get far enough away, their potential energy drops. That makes a lot of sense. That's how we understand gravitational potential energy as well. That's how we understand electrostatic potential energy, is when objects get very, very far away, their potential energy is much smaller than when they're closer together. So it's very reasonable to assume that the potential energy here just drops. And it perhaps goes down to zero at some far distance. And so I think it's safe to say, turn around and go back to infinity. Right? These molecules probably, once they get as close as they're going to get, they continue to go further and further away. They're basically not a bound system. They don't have the correct amount of energy, a combination of position and kinetic energy to be a bound system. They're an unbound system. This was a collision where two objects got as close as they could to each other and then bounced off each other and headed out towards infinity. So that's the answer to D. They turn around and go back, and they probably go out to infinity. Okay, so this has been a solution to the atomic potential whiteboard. I hope it's been clarifying and helped you understand some of these sort of tricky concepts about looking at graphs of potential energy and inferring physical information about them. Not only where the turning points are, where the allowed regions are, but also their behavior. We can actually say stuff like they get as close as possible, bounce off, and then head out to infinity. Or if they get stuck in this middle section, right? If they were in there with that amount of energy, they would bounce back and forth, right? They would oscillate in this region, and that would actually be a bound state of these two molecules where they just got closer, got further, got closer, got further, continuously, forever and ever. Okay, thanks for listening. I hope that has been helpful, and I will see you guys in class.